This is the frequency at which it most efficiently turns sound waves into physical movement. Play a glass its own resonant frequency, but loud, and it may move so much that it explodes. They're using lead crystal, as it's the most efficient at transforming sound into motion.
This lowest peak here is the fundamental frequency, and I'm reading off here 562 hertz. So that's where we should start.
With the computer primed to belt out a pure 562 hertz tone, it's myth-busting time. So this is Mythbusters wine glass breaking test number 1. Simply playing a tone through the speaker to the glass. That's it.
I'm really sorry. I need to actually plug that speaker into something.
Details. Even the Meyer Mythbuster can make mistakes. Let's try that again. Nothing. But in opera, it's not over till the fat lady sings, and Rogers had a harmonious idea.
When you listen to the glass, it has many harmonics above the fundamental frequency. And so maybe it's not the fundamental that breaks it. Maybe we need to produce one of those harmonics.
We're going to talk about harmonics in a second.
Rogers just been playing the fundamental frequency, but there are also many other equally spaced smaller peaks, the harmonics. So this time, the computer's set to blast out the full harmonic sound, an exact match of the glass. Adam also throws a straw into the mix to help see if the glass is moving at all.
So what they're also doing is using a speaker so that they can turn up the volume on it. When you turn up the volume in the car, you don't actually adjust the frequency of the wave. Instead, what you're doing is you're causing greater compression and rarefaction regions. So the amplitude of the wave is increasing. For example, if you're driving in the car and like your jam is playing through the speakers and you're like, oh, let me turn this up. When you turn up the stereo, the pitch doesn't increase in the song. It's not like baby shark do 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 do, and then you like turn it up. I'm assuming Baby Shark's your jam. It doesn't go like baby shark do 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 do, baby shark do 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 do. All that does is it just makes it louder or softer, but the pitch stays the same. So the frequency of the wave, the wavelength doesn't change. Instead, it is the amplitude of the sound waves that is affected when you talk about volume.
Adam's straw dances. This glass really is vibrating. Just check out the high speed. The glass is as wobbly as jello, but not wobbly enough to implode. Back for his encore.
Don't try this at home, kids.
Hey, man, dude! That is a first on television.
Mythbusters exclusive. 556 hertz, 105 decibels, and 20 attempts makes for a world first. History's been made, and it's been captured on high speed. So there's really no need to try this one at home.
Also, super sorry for keeping this browser all the way down there. I just have to make sure I knew what the time was on there. Alrighty. So there we saw the wine glass resonating, or where it was vibrating at its natural frequency, and it had the greatest amplitude of vibration, so much so that it caused the wine glass to actually break. Now, with engineering, I really hope that you guys can see all of these things that I'm screencasting. Otherwise, I'm going to have to redo this whole video. With engineering, if anyone is looking into going to mechanical engineering or civil engineering, anything like that, you really have to worry about resonance in the structures that you create. For example, here is a building where one does not have any shock absorbers, but another does. And this would simulate if there was a strong wind or if there was an earthquake that happens. Well, how is the building actually going to get affected by it? So over here, you can see without any shock absorbers, there's a lot of wiggling, a lot of wobbling that could potentially break if there was an actual earthquake. Over here, it has the shock absorbers. So when the building sways one way, these absorbers are meant to counteract it, and it does not nearly have that great of an amplitude. And if you just Google buildings with shock absorbers, I did GIF. You don't even want GIF. If you look at some images, here are some real live shock absorbers that people have by beams and whatnot. So really, really neat stuff. And this topic is not only important in terms of sound, but also in terms of structural engineering and really anything that gets made. So much so, let me show you one more video here. This is a very famous bridge. It's called the Tacoma Narrows Bridge. And this is an old-timey video, but what this bridge is known for was after it was built, the engineers did not necessarily provide the accurate shock absorbers. So even if it was a slightly breezy day, the Tacoma Narrows Bridge would start to sway back and forth ever so gently. And it'll kind of be like a challenge for people to try and drive across the bridge when it is swaying. On this particular day, there were massive amounts of gusts of wind, high wind, and it was so high that it ended up causing the bridge to collapse. They knew that this might potentially happen, so they shut down the road. They set up these cameras, and here's an actual live feed from 1940.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
What? Like, that is legit concrete. That's insane the way that it's moving back and forth, all from a gust of wind.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
That is pretty wild. And all with resonance. Alrighty. I do miss hearing the bell, I'm not gonna lie. So that is what it means if something is resonating. It finds its natural frequency and it has the greatest amplitude of vibration. With instruments, we want them to resonate because that means that they're playing in tune. With other objects, it could have catastrophic effects. Now, there isn't just one frequency that something would resonate at. The first one that it does is called the fundamental, and that creates the longest possible standing wave within that structure. However, whatever frequency that fundamental is, that's the first time something resonates, that's the fundamental frequency. Every multiple after that is considered a harmonic. So a harmonic is a multiple of the fundamental frequency, and it is the next time that something will vibrate at its natural frequency. So let me show you here real quick. Let me stop the sharing so you guys have a bigger photo. What I have here, some of you might have this at home, this is called a resonance tube. And it is filled with these little bumps. Both sides are open. So you hold it at one end, And when you swing this, you create a pressure unbalance between this, and it forces air to go through this tube. And when it hits all the ridges on the inside, the wave starts to vibrate back and forth. There are compressions and rarefactions made, and you'll hear a lovely little tone. Now, what's interesting about this is the length and way that it's made. It's very easy to get something to resonate. And then if you swing this even faster, we will hear the different harmonics that this will produce. So let's try this out. Let's see how many harmonics we can hit. I'm gonna go very slow because the fundamental frequency is the first time that something resonates at. I don't know if you guys can hear that through the mic, but there's the first one. If I go a little bit faster, there's the second. And I had to swing it twice as fast as I did for the first one. They are multiples of the fundamental. So it's gonna keep getting a little bit faster, but also what do you notice about the pitch? Here's the third. So third harmonic. I have to swing this way faster so the frequency is increasing, and therefore the pitch should also be increasing. There's the fourth one. There's the fifth one. There's the sixth one. That's all I got. And there's my workout for the day also. But super, super neat. As you see, every single time that it hit a different harmonic, I had to go that much faster. They are multiples of the fundamental frequency. So for example, if this was 2 hertz for the fundamental frequency, the second harmonic would be 4 hertz. Third harmonic would be 6 hertz. Fourth harmonic would be 8 hertz, and so on. They're all multiples of whatever frequency the fundamental was at. I'm out of breath, man. This coronation is not keeping me in shape. Whew. Alrighty. So harmonics, they are multiples of the fundamental frequency. And if I know what the value of the fundamental frequency is, it is very easy to find what the first harmonic would be, second harmonic, third harmonic, and so on. And here's a couple of pictures of what we have. So this would be the fundamental, and it has the longest possible standing wave. So with string harmonics, I have to start at a node and I have to end at a node. For the second harmonic, it is twice the frequency of the fundamental. For the third harmonic, it is 3 times the frequency of the fundamental. So tomorrow, Miss Adams is going to talk way more about standing waves with string instruments. On Monday, Kiki is making a video with standing waves that are created in open pipe instruments. And then there'll be one more on open and closed pipe instruments. So the second half of this unit is looking at how instruments vibrate at their natural frequency, how they resonate. Oh, the biggest takeaway that I want you to know is resonance occurs at a very special frequency. And not only does it work for instruments, but any object has a natural frequency that something vibrates at. Sometimes with structures, it's a bad thing if it vibrates at that frequency. Other times, we want it to have the largest possible wavelength. For example, going on swings. If I'm sitting on a swing, there's a very special time that I want to kick my legs out or tuck them back in so that I have the largest amplitude on my swing. If you do it at the wrong time, you're gonna have destructive interference occurring where you don't want it to, and then you're not gonna have nearly as much of an amplitude and you'll slow down. So there's my video. Really hope that the screen sharing worked. Otherwise, I'm going to have to do this again. But other than that, I hope you guys have a wonderful rest of your Thursday, also known as Friday Eve. And I just hope everyone's staying safe, healthy, and you guys are rock stars. I miss you. Keep up the great work, and go Vikes.